In the last video, we took a look at Archimedes' principle and came to the rather surprising conclusion that you can float a battleship on top of maybe a cup of water or something like that if you have a suitably form-fitting swimming pool for it. So now we're going to start to turn our attention to fluids in motion. And to that end, we need to add some assumptions to our ideal fluid. So if you remember before, one of the key ideas that we had with an ideal fluid was that it was incompressible. So we thought of it just being a bag of molecules where you can't change you can change the shape of the bag all you want, but you can't change the volume of the bag at all. Oh well. Now we're going to add to that two additional assumptions. One is that the fluid is non-viscous, which means that there is no fluid drag. Depending on the fluid, this may or may not be a reasonable assumption. Probably one of the most extreme cases of it being not reasonable in daily life I can think of is a Wendy's Frosty. Believe it or not, the density of a milkshake or whatever a Frosty is, don't want to think about that too carefully, its density is basically the same as water. But you ever try to pull one of those up through a straw? It's very, very challenging, and this is because the Frosty has a very high what's called viscosity, which is sort of the fluid equivalent of friction. It means that it drags up against the surface wall, the walls of the surface of the straw, in this case for a Frosty, really hard. And in cases like that, the analysis gets a lot trickier. So if we're keeping things ideal, we say that the fluid has a very low viscosity. And we'll just assume that's non-viscous. All right, and then the other one that's maybe a little trickier is we assume that the flow is laminar, which means that it can flow in streamlines. Now, what do I mean by that? If you've ever seen like photos where they've stuck an airplane wing into a wind tunnel to test it, what they'll do is they'll put little bits of they'll inject little bits of smoke so they can watch how the smoke goes around the fluid, around the airplane wing. And say if the smoke is coming in along here, what they'll notice is it kind of just neatly bops around the airplane wing like that. If they bring it in maybe a little closer, it does that. Oops, tailing out back there. If they bring it in like this, it maybe does something like that. You get the idea. And the idea is that basically any adjacent molecules will tend to follow right next to each other. And everybody just moves around in a nice orderly manner. Now, to take our airplane wing analogy a little further, we can get to a regime where the flow around an airplane wing is non-laminar, and this is usually considered a really bad thing. So if you're at a particularly high angle of attack like this, so say the air is flowing in like this, what will happen is when you get to the back side of the wing, it turns out that you don't get a smooth reconnection. Instead, you just get a whole bunch of turbulence back here. And this turbulence is associated with a loss of lift on the wing. Now, loss of lift on a wing attached to an airplane is usually considered a bad sign. It's unusual attitudes are one of the main reasons for airplane crashes. And it's because if you get into these attitudes, you can create these bits of turbulence around the wing. You can also have the same thing happening if the air is moving too slowly over the wing. It won't reconnect smoothly behind the wing. And so that's why you see all those crazy arrangements of flaps and slats and stuff like that, is they're designed to help coax the airflow around the wing in a way that maintains laminar flow and thus lift as the aircraft is slowing down. By the way, assuming that a plane is correctly flown in, every landing is technically a crash landing. It turns out that when you go into the final phase of the landing, you do actually intentionally put it into an attitude where you lose your lift and you technically crash into the runway. The whole idea is you crash into the runway from a height of well under a meter, and that's something that the shock absorbers in the landing gear can handle readily. All right, so on that cheery note, let's think about the consequences of these assumptions. So, just as a bit of a thought experiment here, have you ever, say, taken a garden hose, run some water through it, and then stuck your thumb over the end of the hose? If you have, what happened to the speed of the water? Okay, hopefully you agree with me that the speed of the water increased. So why is that? Well, this is what we call a constriction. So let's say we've got a pipe, and then this pipe hits a constriction over here. Let's think about what that means for the speed of the fluid. So the incompressibility means that if, say, in some amount of time, delta t, so I'll call this A1 here, the fluid in the fat part of the pipe moves through some distance delta x1, right? Whatever this volume is right here, in that same amount of time, that much fluid had to move through the skinny pipe. But since this area here, A2, is a lot smaller, this length here, delta x2, is going to have to be a lot longer to compensate. So in order to have the same volume of fluid go through in the same amount of time, the rate at which the fluid goes through in units of volume is called the volumetric flow rate. This would be equal to this area. And to get a volume here, I'll times that by delta x, and then to get a rate, I'll divide by delta t. So this turns out to be equal to the cross-sectional area times the speed of the fluid. And the units of this are typically given as cubic meters per second or liters per second, but keep in mind there are 1,000 liters in a cubic meter, so be careful about your unit conversions. Okay, so let's say this is region 1, this is region 2. So what this is going to mean here is if this is the fluid here is going at speed v1 here, it's got to be going a heck of a lot faster over there for our speed v2. Alrighty. So the incompressibility is saying that since the volumes have to be the same, we have to have the same volumetric flow rate. So the assumption of incompressibility is that Q1 equals Q2, and yes, I know we used Q for heat not that long ago. This is standard notation. We now have A1 V1 equals A2 V2. All right. So you might also ask yourself, well, great, what if I have branches? Like I could imagine a river that has branches or something like that. Well, in general, if we have some sort of a junction of fluid flows, So we'll call this Q1, let's say it's flowing into the junction. Fluid is flowing into the junction over here. That would be Q2. Let's say it's flowing into the junction over here. We'll say that's Q3. Let's make it outbound over here. This would be Q4 going out. Let's say it's outbound over there. Q5 going out over here. What you're going to require is that Q in equal Q out. So in this case here, that would be expressed as my inbound flows Q1 plus Q2 plus Q3 equals Q4 plus Q5. And by the way, this sort of thing shows up in a whole bunch of really weird places that you might not realize. For instance, in the study of traffic flows, this would be an intersection. And so this is saying that, on average, the number of cars that enter an intersection every minute or hour or whatever have to equal the number of cars exiting, or else you've got a problem. This also shows up in electricity, where this will get called Kirchhoff's node rule. And that basically is just saying that the number of electrons that go into a junction in a circuit in any amount of time have to equal the number going out, or else there's a problem, etc. So this is a sort of thing that tends to show up in a lot of different places. All right, so maybe let's just do one quick example to make that a little more concrete. Let's say here we've got two rivers. So river number 1 here, let's say, has a volumetric flow rate of 5,000 liters per second, and river number 2 here flowing in is carrying 1,000,000 liters per second. Let's say over here the river is 150 meters wide, and that's 10 meters deep. And so we would ask, what is the speed of the current in river number 3? All right, so following that through, we can say Q3, that's the outbound flow, has to equal the sum of the inbound flows, Q1 and Q2. Q3 is also equal to A3V3. So this would be equal to Q1 plus Q2. So V3 is Q1 plus Q2 over A3. And since I gave you the length and the width, this will become Q1 plus Q2 over the length of the river times the width. Okay, we can figure that out. So we'll have V3 is equal to, all right, we have 500,000 liters per second there, plus 1,000,000 liters per second there, over 150 meters wide times 10 meters deep. All right, now you got to be careful here. Keep in mind that liters are cubic decimeters, not cubic meters. So you've got to convert your liters into cubic meters. So 1 cubic meter is 1,000 liters. So we can go ahead and do some cancel action here. Cancel, cancel, cancel. We can lose 2 powers of meters off against that. We can lose 3 zeros here and here against that. So I have 1,500 divided by 1,500 to get that the speed of the current in river number 3 is 1 meter per second. Okie dokie. So in the next video, we'll be taking a look at Bernoulli's equation, where we'll actually see how the rate at which a fluid is flowing affects the pressure of the fluid. Catch you in the next one.